Welcome back, Physical Science 20. This is the last lab in the HT2 booklet. This is lab 16.2, heat of combustion of candle wax. So with the previous lab, you looked at the heat involved, absorbed or released when we had dissolving or a chemical reaction in terms of an acid and a base. This time we'll look at combustion and measuring the energy involved with that. So if we take a look here, the amount of heat released by the complete combustion of 1 mole of substance is defined as the heat of combustion, or delta H COMB as a subscript. The amount of heat released may be measured in calories, the older way, or in joules, the newer way. A calorie is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree C. The SI unit for heat is joule, and 1 joule is equivalent to 4.184 calories, as we've seen earlier. If a sample is pure carbon and it's burning oxygen, the reaction is simply this, carbon, and of course you need oxygen, and it makes CO2. The enthalpy of combustion is 393.5 kilojoules, and it's negative, meaning, of course, energy is released. And with all combustion reactions, we see that happening. So here's some other ones. So methane, here's the molecule, there's the energy associated, propane, butane, octane. And a little hint here, if you look at the molecule here, the more atoms we have in the molecule, the more energy released. That's one of the questions later on will allude to that. So in this activity, you'll calculate the heat of combustion of a fuel in a candle. The burning candle will heat a measured quantity of water. Using the specific heat of water, the mass of water, and the increase in temperature, you can calculate the amount of heat released by the burning candle using the relationship Q is equal to MC delta T, as we've seen earlier. Okay, so the idea here, of course, is that we're going to have a somewhat closed system, and all the energy released by the candle will be used to heat up the water. So if we're assuming a perfect conversion there, that energy is equal to the energy required to add to heat up the water, which is equal to the energy released by the candle. Okay, so here, instead of using this specific heat, we'll use this. My arrow is off a bit here. It should be pointing to this. So the specific heat of water, 4.184 joules per gram degree C. Okay, there's a list of materials there. Problem: how can we measure the heat released by a burning candle and calculate the heat of combustion of candle wax? Other objectives: measure the change in temperature of a mass of water during combustion, calculate the amount of heat released during a combustion reaction, and then calculate the energy released per mole of reactant during a combustion reaction. And the materials, the setup is a little complicated, but I'll hopefully have one set up so you can see what it looks like, and you'll be able to easily do that. So we have a large metal can, the candle's enclosed in there. It's off the ground a bit so that oxygen can flow up here and involve the candle to be lit up, and then the water will be in a smaller can here. Okay, safety goggles, of course, as usual. And we're using alcohol-based thermometers, so we don't have to worry about mercury. Before you do the lab, I'd like you to do the pre-lab as we usually do. You can just do it on loose leaf. So define heat of combustion and also calorie. You'll find the answer for that on the previous page. State the relationship between calories and joules. And B, change this to joules. What is the relationship between joules, mass, and change in temperature and specific heat? Huge hint on the previous page. Number 3, kind of relating to what we've talked about before, define exothermic and endothermic reactions. What is the sign of delta H for an exothermic reaction? What about for an endothermic reaction? So you may have to look back a few pages if you don't remember that, because we did discuss that. Omit number 4. Number 5, read the entire laboratory activity. Form a hypothesis about how to measure the amount of heat released in a chemical reaction. Record your hypothesis. So just kind of describe basically what was mentioned over here. How, in fact, are we going to do that? How are we measuring the heat released by candle wax? It's kind of a sneaky way involving water. So just kind of quickly explain that in a sentence or two over here in the area set aside for the hypothesis. And then procedure. So light a candle and drip a few drips of molten wax onto the lid. So here I just have a can lid. If the candle is not stuck to it already, we'll do that and just stick it to it by melting some wax and sticking the candle on. Don't worry about number 2. Number 3, determine the mass of the candle and the lid. Record this on the data table. So I need the initial mass of the candle assembly. And then number 4, refer to the figure 4 as you set up the apparatus. Unbend 3 paper clips so that they form an S hook. Use the paper clips to attach the can to the ring. So that's this part right here. So you see the paper clips. To attach the water can to the ring, we just use paper clips there. So I have pre-drilled holes in the can, so it should be relatively easy. Position the candle assembly under the can and adjust the ring so that the bottom of the can is about 4 or 5 centimeters above the top of the unlighted candle. So that's this distance right here, about 4 to 5 centimeters. Unhook the small can, measure the mass of the can and record its value. So we need the mass of empty can right here. And let's see, next. Measure and record the data, the mass of can and the water. Oh, after we fill the can about half full of distilled water. Try to use distilled water from the blue jug. And then, of course, we want can and water massed. So empty can, mass of can and water, subtract, and you get how much water used in terms of mass of grams. Place the large can over the candle, raise the large can off the base of their stand and insert 4 nuts. Instead of using that, I just have stoppers so to raise this up a little bit so once again air and oxygen can be exposed to the candle. 11, record the initial temperature of the water. So we want the initial temperature of what the water is. It shouldn't be too far because it's been sitting at room temperature in the blue can. And let's see here. Immediately replace the small can of water to its previous position once the candle is lit. While the candle heats up the water, gently stir the water with the glass stirring rod. Continue to burn the candle, and I change this until you think the temperature has risen enough. Now I'm thinking about around 15 degrees or so. So once the temperature has gone up a fair amount, record what that is, and then blow out the candle. Record that final temperature, so that highest temperature that you saw it was. And of course that's going to go over here. The initial temperature water, final temperature, subtract, you get the difference. And then lastly, once it's cooled off, measure and record the candle assembly. And we're not going to worry about repeating it a second time. We'll just simply do it once. So once you have the final mass of the candle assembly, of course it should be a lot lower than the initial one because the candle has burned, right? So we're looking, and then subtracting here will give us the mass of candle that was burned. So we know how much candle was used up to supply the energy. Okay, so once you have that, we're not going to worry about this, doing it at a different distance, simply this. Number 1, calculate the number of, let's change that to joules of heat absorbed by the water. So Q equals MC delta T. We know the mass of water from here. We know the specific heat capacity of liquid water and the temperature change of water. And if we're assuming all of that energy came from the candle and none was lost, even though obviously some heat was lost, but we'll assume it was a complete conversion, calculate the heat released per gram of candle wax. So whatever we get here for joules, of course, that was supplied by the candle wax, the amount of mass that was burned. Okay, and then, from here, assume the formula for wax in the candle is C32H66. You can see wax is a fairly big molecule. Calculate the molar mass of wax. So do that over here. Calculate the answer for molar mass. Number 4, the equation for the combustion of it, assuming complete combustion. Give you a hint here. Here it is right here, C32H66 plus O2. And if it's complete combustion, we just get CO2 and H2O forming. And if you look at this, if we just use one molecule of C32H66, the balancing works out like this. We need 48.5 oxygen molecules, 32, 33. To make this a whole number, I just doubled by 2 here. So 1 times 2 is 2. 48.5 times 2 is 97. 32 times 2 is 64. 33 times 2 is 66. So that's actually the balanced equation right there. Calculate the number of, change this to kilojoules of heat released per mole. So we want to get it in the same unit as we see over here. So we can compare candle wax to heat of combustion of these other substances, and of course that's unit of kilojoules per mole. So up until this point, we have joules per gram. So to change joules per gram to kilojoules per mole, you can see here multiplied by the molar mass, grams and grams cancel. I'll have joules per mole. but of course I want kilojoules per mole. So divide by 1,000, joules and joules cancel, and I have my unit of kilojoules per mole. And once you have that number, you'll be able to compare with these numbers over here for methane, propane, etc. All right, and lastly here, compare the heat of combustion you obtained with the values on those items I just showed you. Explain any trend you observed. At the start of the video, I gave you a hint as to what to look for there. We can omit number 8 because we didn't do 2 trials. Explain possible sources of error. And of course, the big thing here is that when we do a question like this, we're assuming 100% of energy conversion from candle wax to heating up water. Is that true? So you can talk about that, other things, etc., that you may have noticed. The real-world chemistry, explain why it is recommended that people travel by car in cold climates carry a candle and matches as part of an emergency survival equipment. And then 2, diesel engines are often used in large trucks and heavy equipment because the diesel fuel molecule produces more heat than gasoline. So knowing that diesel fuel produces more heat than gasoline, what does this imply about the nature of the molecules of diesel fuel compared to that of gasoline? Okay, so you should be able to answer that by looking at the trend you observed in the previous question and this chart here. All right, so that is Lab 16.2, heat of combustion of candle wax. See you again.